To jump right in, I'm sure you, like many bridge owners, similar to the Arizona DOT, have a number of bridges that exhibit cracking, whether it's stress-induced cracking or distortion-induced cracking, a very common problem in Arizona, like many of you is experiencing that as well. This particular project, they chose 4 bridges that they had concerns about. For a long time, for about 20 years, these bridges have been exhibiting cracks. Some of them have up to about 100 cracks. The bridges are known as Virgin River Bridge number 1, number 5 northbound, number 5 southbound, and Virgin River Bridge number 7. The cracks vary in nature. As I said, some are distortion-induced, some are stress-induced. Some aren't that significant. Others happen in high-stress zones, stress-induced cracks in high-stress zones, and those are very, very concerning. Numerous attempts over the years have been, rehabilitation efforts have been carried out to address this cracking. Some of the cracks continue to form, new ones continue to appear, so Arizona wanted to do something to address this. Another challenge with these bridges is that they're located in a very remote section of the state. It's about an 800-mile round trip for the inspectors in Phoenix to get to these bridges, do what they need to do, and get back to them. There's no alternative route through the Virgin River Gorge, bridge number 1, 5, and 7. It's about a 29-mile stretch that runs just between St. George, Utah, and Mesquite, Nevada, on the Nevada border. There's really no economic benefit to the state of Arizona from these bridges. I think there's just one exit in the state. This rural section of highway, when it was built, was actually was the most expensive section of rural interstate at the time it was constructed. The cost in the 60s and 70s when it was built was $10 million a mile, which by today's cost is $60 million a mile, which is about $1,000 an inch. It's also on a very important transportation corridor. Interstate 15 is also part of the Canamex corridor that brings goods, freight from Canada to Mexico and back. The ADT is around 18,500 on this stretch of interstate, and it's about 39% truck traffic. So very important infrastructure assets. So faced with these challenges, ADOT wanted to answer this question. Could they utilize a structural health monitoring system to help assess the conditions of the bridges and provide them remotely provide them information on their condition? Today, Ashton and I are going to touch on the background information on these bridges, the funding process that ADOT went through to get this work completed, as well as the modeling that happened of the bridges, as well as the load testing itself and the development of the long-term instrumentation plan. ADOT applied for a grant in 2016 from the Federal Highway Administration. This Accelerated Innovation Deployment Grant. The FHWA allocates about $10 million a year in this program with the intent of they want bridge owners and transportation asset owners to deploy technology it's been proven, but they aren't currently utilizing it. That's the purpose of these grants. Those red dots represent different states and projects where these grants have been used to date so far. ADOT established these goals during their grant writing process. The primary goal, they wanted to understand the true behavior of each bridge through both modeling and testing. They also wanted to be able to monitor these bridges from Phoenix to save that 800-mile round trip drive and greatly reduce the cost and the use of on-site inspection staff. And finally, they wanted to provide themselves with additional decision-making tools so they could make data-driven decisions about what the best options are for the rehabilitation or replacement of these structures. I'm going to go into a little bit about each one of the bridges now. Bridge number 1, these all were constructed in the 60s and 70s, all the same age roughly. This particular structure is 5 spans and 4 girders, and it has nearly 100 cracks in it that have been appearing for about the last 20 years. The majority of these cracks are distortion-induced and aren't that serious. A few of them, though, most of them appear in the tops of the vertical stiffeners, in the weld between the connection between the vertical stiffener and the underside of the flange. There are some cases where these cracks have towed down and continued down into the web area. Many of these have been drilled out. Some of the cracking has progressed to the other side of the drilled out holes, and new ones do continue to form. This figure, each one of those little symbols indicates where one of the cracks are located. So throughout the bridge, the mechanism of how they've been formed is pretty well understood, but there are a lot of them. The bridges number 5 northbound and number 5 southbound are twin girder, what used to be called fracture critical bridges, but after yesterday we don't do that anymore, I guess. So, but twin girder bridges with hone type details. Some of the most concerning cracks on these 4 bridges are on these 2 bridges. They actually are stress-induced cracks that appear at the end of longitudinal stiffeners in tension zones and areas where there are stress reversal. ADOT has drilled out those cracks whenever they do find them, but it was one that, of all the cracks to monitor, some of these are the most concerning from a bridge safety point of view. Once again, those are the locations of the cracks. There's certainly not as many as on bridge number 1, but as I said, the nature of the cracking on these 2 bridges was more concerning than on the other bridge. Bridge number 7 is interesting. When it was originally constructed, it was 2 independent 2-girder bridges. In 2006, they added 2 stiffened girders down the center of the structure so they could widen it, and the deck was made composite over the entire structure. It's interesting in the fact that you still have, the girder spacing is 18 foot 6 inches on the original girders, so you have a very flexible external girder and a very stiff inner core on this bridge. So one of the things we were really interested in the modeling and the testing was to see how that influenced the behavior of the bridge. One of the things that's causing the cracks on this bridge is large differential deflections between the girders and the associated out-of-plane distortions caused by the lower lateral bracing members. Most of the cracks appear over the piers on this particular structure, once again, due to the out-of-plane distortions caused by the lower lateral braces. When we received this assignment from the Arizona Department of Transportation, we realized that many of the things were outside of our core area of expertise. So we brought Bridge Diagnostics on board. They specialized in instrumentation and testing of bridges. They in turn brought Metal Fatigue Solutions, MFS, onto their team. They make some specialty fatigue crack sensors, and we'll discuss a little bit about those later. ADOT, their local districts provided tremendous assistance to us in terms of the traffic control and coordination and scheduling. The Virgin River Gorge, it's a very, very beautiful area, and the bridges had lead paint on them. So we had to come up with a lead paint abatement plan and bring on a specialty contractor we removed paint everywhere we were installing gauges, and we had to mitigate that, and Southwest Hazard Control handled that for us. We used a snooper as well as climbing for the installation of equipment, and lots of traffic control that was provided by the Arizona Department of Public Safety as well as Road Safe. The timeline, the phase 1 load testing and modeling, we started the actual work on the project in last September, October, and we applied the instrumentation and did the load testing in January. We're finishing up the reports and the development of the long-term monitoring plan now, and we'll have our second round of application of the long-term monitoring equipment later this year. Today we're just going to touch mainly on the phase 1 task and the development of our plan for the long-term modeling. This involved document review, the generation of the finite element models for each of the 4 bridge structures, the preparation that went in before we actually went out and did the instrumentation and modeling. Ashton's going to touch on the diagnostic live load testing and the results of that, as well as their installation of that equipment in the field, and then an analysis reporting phase. We started with document review. We set up a Dropbox kind of team site with all these different players on board. We've been inspecting these bridges for the last 20 years, as well as have done load rating of the structures and some rehabilitation projects on them. So we set up a Dropbox site with repair plan details, old inspection reports, so we could all readily share that information. Our bridge engineers at Burgess & Nipel started developing the finite element models for each of the 4 structures. BDI has some proprietary software that works with STAD Pro, where after we actually do the field load testing, we could then calibrate these models so that the behavior in the computer matches what we saw in the field. We could then use those models to identify high-stress areas within the bridge, so we would know from a targeted perspective where were the best places to place the instrumentation, as well as the areas that were of most concern. One of the big task on this job was just dealing with the maintenance of traffic operations. I've been a bridge inspector for many, many years and always taken lanes here or there for various tasks, but this was the first time I had been involved in purposely trying to shut down an interstate in both directions simultaneously. It's amazing how many people need to be called when you're going to do that. But that took a long time, had a lot of help from other people at Burgess and Nipel. We needed to have empty bridges for the testing so we could run our controlled bridge test. We were allowed to do rolling closures, which involved multiple police officers, one rolling out 4 or 5 miles away for the bridge at 5 or 10 miles an hour to slow traffic down, and then we would clear traffic between them and the bridge, and that would give us about a 10-minute window each cycle to perform the testing, and then we would kind of repeat that 5 or 10 times during the course of the day. We weren't allowed to back up traffic into the adjoining states, Nevada and Utah. We had very limited cell phone service on some of these bridges, so coordination of all these different people blocking ramps and slowing down traffic was an issue. There was an ongoing construction project between 2 of the bridges that we had to kind of work around and coordinate with, and in my infinite wisdom, I scheduled all the field work over a holiday weekend. So there was a 2-week period we were doing all this instrumentation, and I didn't realize one of those weekends was a holiday weekend, and that caused all kinds of other issues too. So I should have checked my calendar first, and I didn't. So some of the resources we needed to deploy to manage all this traffic, we had permanent variable message signs that had to have notices up a week or 2 in advance of the work. We had daily variable message signs that needed to be out there to inform the traveling public of what we were going to be doing. As I said, we had multiple Department of Public Safety, essentially Arizona's version of the state police officers out there to help us control traffic. We had a maintenance of traffic firm that was helping us, and then ADOT's North Central District provided a large number of personnel to help us out to close down ramps and assist with the maintenance of traffic. They also provided us a dump truck and a driver to use for the controlled load testing. With that, I'll turn it over to Ashton.
Thanks, Mark. So for the basic, now that we've got all the general information about the project, for BDI's main goal for the structural testing and live load testing and development of a phase 2 monitoring system was to capture the overall structural behavior in the primary girders and investigate possible causes for the cracks. And the key factors for our live load testing is we have to record continuous data with no other traffic on the bridge, install enough sensors across the bridge in a cost-effective manner, and then also we had to look at specific areas where there was the cracking, so we had to add instrumentation in the development of our instrumentation plan just for that. So going on, for bridge number 1, in this development, we can't instrument the entire bridge, but this is the one with a lot of cracking, so we had to focus on at least the first 3 spans. So each span, we put sensors at the mid-spans near the piers to monitor the peak stresses from the moments, along with support behaviors and looking at what the bracing and the diaphragms had effect on the possible cracks. So in total, we put about 92 sensors on this bridge, 8 of these being crack check sensors provided by MFS. They were located in between the vertical stiffener and the top flange. In this next screen, I show just a typical instrumentation cross-section. We instrument both top and bottom of the beams. This helps with calculating the neutral axis of these beams and then verifying composite behavior between the deck and all of the superstructure. So, and then also, along with the primary girders, you can see that we've instrumented the diaphragm points heavily here, looking at why and what are the forces induced into the primary girders based off of the results from the diaphragms. Moving on, bridge 5, northbound and southbound, very typical instrumentation. Same, we didn't instrument all 3, we instrumented the first 2 spans, mid-span, near piers. We wanted to focus on the lower lateral bracing, longitudinal bracing, because that's where the significant amount of stress cracks are. So on this bridge, we actually instrumented 4 of the cracks, 3 of them being repaired cracks. I think one of them was a cutout, a weld repair, and also a drill out, I believe. So on the next slide, I showed another typical instrumentation. This is a two girder system. Instrumenting top and bottom again, and you can see we've instrumented those lower lateral braces. Same type of instrumentation, another typical detail from our cross sections, top and bottom. Accessing all this, we had to be on ropes, climbing across the girders. It was quite the obstacle, along with help from the U-bit snooper truck. Bridge number 7 with the two new weathering steel beams down the center of the bridge. We wanted to look at what the effects were from that and how stiff it was comparatively to the rest of the bridge. Also, we instrumented heavily on the diaphragm point above the pier where the cracks are forming from that stiffness. Typical cross sections again. This one on the far left of the screen is actually instrumentation that we did. It's a significantly larger diaphragm there, a lot stiffer, so the cracks were actually forming between the gusset plate and the web there on that one. Like I said, for all of this data, we used our BDI built in-house strain gauges. They're a 3-inch reusable strain gauge. They're attached to the structure with removable tabs. These tabs are then glued on the structure. Easy, they can be installed in less than 5 minutes, so it made it perfect for this type of testing. They're good for live load, high-speed tests. They're not really designed for monitoring, but for this type of testing, they are the perfect application. Here's some typical installations. For this entire project, like Mark had said before, Burgess and Eipel and BDI would access the bridge via rope or the snoop truck, mark all the locations, and then Southwest Hazard had to come back in, remove all the lead paint, and then we went back out after all that lead paint was removed and installed the sensors. I think in total we did the first two Bridge 5 and northbound and southbound in about 3 days. We installed, tested, and removed all the sensors and then moved on to Bridge number 1. That one took a little bit longer. There's a lot more sensors on that one. Along with our strain gauges, we have our rotation sensors. These sensors are used mostly for comparing global response to the bridge. They're attached and installed near abutments and piers to get that global response of the structure in comparison to the strain gauges. We used half-degree tilts on this, really precise movements. The bridges aren't moving that much. And here's just a typical installation. Mark out the locations, paint was removed, and we installed those also with our removable tabs. So easy installation, go on in less than 5 minutes. All these sensors are then attached to BDI's STS-4 system. It's a Wi-Fi data acquisition. Each node has 4 channels, so it can collect four sensors. Each sensor has its own, what we call an IntelliDucer. So basically it makes a smart plug, so you don't have to track any wires. It saves the name of the sensor, so when it loads into the software, it automatically applies its calibrations, its excitation voltage. All of the parameters that you need for that sensor are already there, so it's really easy plug and play for our, we're not electrical engineers, we're civil engineers, so it makes it nice and easy on us. Here's a basic diagram of how our system works. All of our nodes are spread out across the bridge. The Wi-Fi system has about a range of about 1,000 feet, so these are big bridges, so we're kind of stretching our limits here, but everything ran really smooth throughout the testing out there in Arizona. Try not to slow down traffic or having to close down or do those rolling stops as much as possible. All that data acquisition is then collected on our in-house built-in lab view, STS Live. It makes it really nice and easy so we can program it to fit our needs. Like I said before, it automatically recognizes all the hardware, so all those calibration files come right in. And then there's a real-time display, so I'm able to look at the data and see if there's any abnormalities and if the structure's acting in a linear, elastic manner, returning to 0 after each test. Here's the typical live load testing plan. Like Mark had said, we had to close down traffic with our rolling stops. We had 6 paths. We had to run them twice. The truck rolls about 5 miles per hour, and we keep track of the truck where it's positioned across the bridge with a encoder. We ran a minimum of 2 tests each path just for data review processes in the end. Along with our live load testing, we ran ambient data, ran about 3 tests at 100 hertz for 10 minutes throughout the day. This data is going to be utilized for looking at how we want to develop our phase 2 monitoring system. After all the testing was complete, we then removed all of the sensors and covered it up with galvanizing steel paint. Along with our sensors, we brought on metal fatigue solutions. They provided us with an electrochemical fatigue sensor to detect active crack growth. In total, we installed about 15 crack check sensors on existing documented recent inspections, and also on 4 repairs. From that data, we actually collected from the 15 crack locations, 4 with active growth, 5 not in active rain but showing pre-growth, and 6 not actively growing anymore. And from the repairs, we had the weld repair was unsuccessful. Drills where one was successful, one was unsuccessful, and the cutout was successful. So through their data, we actually can bring in what we want to look at for the long-term monitoring afterwards. After all of the data has been collected, we do our data review. We look at the sensors like I talked before. We run 2 tests per path. So we can look at the data afterwards, making sure that we can see that there's no gauge malfunctions, sensors are acting the way that they should, we're seeing reproducibility and linearity, sensors are returning back to 0, so we're not seeing any yielding. Along with reproducibility, we have to look at expected behavior. You can see the blue line here, that's actually a bottom gauge at mid-span. It's going into compression while the load is on the adjacent spans, and then peak tension when the load is directly above. The green line there is actually representing the top gauge, and you can see that it's got smaller responses, which actually means we place the sensor near the neutral axis, which is verifying composite behavior between the deck and the beams. Here's a nice image of our lateral distribution. So we've got all 6 load paths on there at a mid-span location, so you can see when the truck is on one side of the bridge what it is doing on the other side of the bridge. It's just a nice image of what distribution we have throughout this one. This is actually from bridge number 7. Along with the primary girders, we looked at those crack locations and the diaphragms. So this actually is diaphragm location where we have one that's cracked and one that's uncracked. There's no noticeable difference between the two, so it's acting normally as expected. After data review was complete, we completed our modeling. We got all of our models from Burgess & Nyepel. They performed all their models in STAD. We then verified, reviewed, converted them into Strand 7 for our purposes. That's what our engineers and analysis engineers use. And then with our proprietary software, BDI Morph, we calibrate the model using an integrated approach, which I'll talk about now. So integrated approach is basically taking field data that we've collected out there and then creating, with our finite element model, we then, through an iterative process, we adjust those parameters like deck stiffness, eccentricities, and restraints until that model mimics the data that we collected in the field. And that can actually be used for load rings, which will actually be taking place in phase 2. So after all that, so interim conclusions after phase 1, there was no major signs of distress. Bridges are acting as they were expected. All that diaphragm data that we collected will be used for the phase 2 monitoring. And we now have an understanding of some of those cracks and what they're actually doing. Phase 2 monitoring, it's going to be a long-term monitoring plan. It's currently in development. I'll go over a few of the options that we're thinking about in the next couple slides. Installation is planned tentatively for October 2017 with a duration of about 12 months. Hoping to use all of the phase 1 testing plans and data to guide us on our selection and designing where we want to put sensors for the monitoring system. So the 4 levels of structural health monitoring are detect, locate, quantify, and predict. For this project, we really want to nail detect and locate. Quantify is our main goal. We'd like to quantify what the damage is of an existing quality of this bridge is right now. But with our instrumentation and costs, we may have to lower our expectations and just do a detect. We can detect where there's damage and cracks growing and locate where possibly that is being affected by. Predicting is still very academic and is still in development, and cost would be prohibitive. So phase 2 monitoring, these are some of our options. Lower lateral bracing instrumentation near the piers and abutments on bridges 5 where we have those stress cracks growing. Fatigue crack growth where we could utilize MFS's permanent system. And then comparison between cracked and uncracked sections through a long-term monitoring. We also are talking about acoustic emission systems, And then we also have live camera feeds on the bridge with environmental data, vehicle characterization.